I'm going to be talking today about some work that I did several years ago on the Gulf of Mexico. So this is sort of a case where the research started one way with sort of some very particular goals, and it ended up somewhere kind of unexpected. So several years ago, I started to structurally restore several large crustal scale cross sections in the Gulf of Mexico. And at the time, I was pretty new to structural restoration. So when I kept running into the same problem over and over again, I figured it was user error. I was doing something wrong. And the problem I kept running into is that the sections, these cross sections, they never restored to the correct bathymetry. Not a single section that I looked at, and not by just a little bit. They were off by several hundred meters. So what I'm going to talk to you about today is the journey I went on trying to make sense of this several hundred meters of anomalous vertical movements in the Gulf of Mexico. So I'm going to start by introducing you to this basin. The Gulf of Mexico is a passive margin rift basin that formed during the Mesozoic breakup of Pangaea. In the Triassic, Pangaea rifted in a northwest-southeast direction as South America moved away from North America. And thick salt was deposited around 165 million years ago. And this happened around the same time that the tectonic extension transitioned to this counterclockwise rotation of the Yucatan. And this was primarily accommodated by seafloor spreading. And the seafloor spreading ceased in the early Cretaceous. So the present tectonic configuration of the Gulf of Mexico was really established about 140 million years ago. So what we have is an extensional passive margin basin with highly extended crust that transitions to oceanic crust. So these lines here illustrate the approximate limit of oceanic crust. That's sort of this yellowish white line here is the limit of oceanic crust. And then you can see the extinct spreading ridge and the transforms. This study is going to be focused in the eastern Gulf of Mexico, encompassing both the Yucatan and Florida. I'm going to show you sort of a cross-section from this area here, offshore Florida, to give you a sense of the stratigraphic configuration. So this basin contains up to 10 kilometers of sediment, including several kilometers of mobile salt that facilitates gravity-driven salt tectonics. The Cenozoic section is dominated by siliciclastic deposition, and in contrast, the Mesozoic is dominated by carbonate sequences. These Mesozoic carbonates are particularly prominent along the Florida and Yucatan platform. So you can see in this Google Earth image up here, the bathymetric expression of the Florida platform. These are very long-standing features, and they're important because these are mostly platform carbonates. And platform carbonates are deposited in clear, warm, shallow water. So they provide really nice paleobathymetric markers throughout the course of the restoration. As I said, this study is going to be focused in the eastern Gulf of Mexico, which provides the benefit of slightly less structural complexity than elsewhere in the GOM because there's no big salt canopy over here like there is in the central GOM. So I worked on 4 cross sections, 2 from the US and 2 from Mexico. And my original research goal was to reconstruct the paleogeography of the original salt basin and the rift-to-drift tectonics for this conjugate margin. And these cross sections are currently at pretty high angles to each other, but remember that this extension involved a large degree of rotation. So prior to the rotation of the Yucatan, these lines were approximate conjugates, not perfect. The interpretation of each section, here's those 4 sections, is based on 2D seismic images supported with 3D seismic where it was available. The stratigraphy and the lithofacies are based on more than 1,000 well bores from around the basin. So at each, just to give you guys a little bit of background on what structural restoration entails, at each step of the restoration, we have to apply several corrections. So first, we backstrip and we decompact the sediment. And the decompaction is based on details of the lithology that's, we get from all the wells that have been drilled out here. So for example, mudstone compacts more than sandstone. So we have to pay attention to that. These are really long lines, several hundred kilometers. So we have to consider flexural isostasy. That's also considered at each step. And it's an extensional basin. So we have to consider thermal subsidence. For the thermal subsidence, we use a spatially variable beta factor to calculate it. And that's actually based on crustal thickness measurements from the seismic data. And then we also do, move, unfold, and unfolding, and sort of all this classic structural restoration steps. So I started this restoration process. All right, so here's one of these lines at the present day. And at each step, I go through and I backstrip each unit, decompact it, apply the thermal and the flexural corrections and a sea level correction. And everything was going fine as I did this until I got all the way through the Cenozoic, through the late Cretaceous. But when I got to the base of the Cretaceous and then into the Jurassic, I kept having this problem, which was that after applying all of my corrections, the proximal part of the section, which is up here, was not sitting at sea level. And I know it's hard to appreciate because this is a very long line, 200 kilometers, but you can see how this is sitting about 1 kilometer below sea level. So, it's really not even close to sea level. And we have really good constraints on the paleobathymetry of these rocks. It's carbonate platform, it should be at or very near sea level. But again, initially I thought, okay, well, I'm just doing something wrong. So I just translated it up and kind of kept on going. And then I had the problem again throughout the Jurassic where I kept finding, well, this is just really not sitting at the bathymetry that it's supposed to be. So basically from the early Cretaceous all the way through to salt deposition, I kept having to apply this vertical correction to get this section to the bathymetry demanded by copious stratigraphic evidence. I'm going to show some 1D subsidence plots. So I undertook this subsidence analysis. I find the 1D subsidence plots a little bit easier to sort of take in than the 2D ones, but this is based on the 2D restoration. So it has all those corrections applied that I mentioned. And this is from a location up on the carbonate platform where this star is. So it's not influenced by salt tectonics. Salt tectonics is not going to be driving the observations here. So you're looking at depth here on the y-axis, and this is age on the x-axis. So as you go back in time, this is all the different horizons that I considered throughout the restoration process. So, right, so these are the uncorrected lines as I went through. You can see top Cretaceous, everything's fine. Here, these circles represent where those sediments should sit. Like this is the correct bathymetry. So this is a discrepancy. This red arrow represents that discrepancy. So the dots indicate the bathymetry dictated by the geology, and this is that anomalous subsidence or anomalous vertical movements. It's on the scale of several hundred meters. And I'm observing it not just on one section, but on every single section that I looked at. So when all is done, I'm looking at 600 meters to honestly up to 2 kilometers of these anomalous vertical movements. These 1D subsidence plots are nice for showing the cumulative effect through time, but I want you to get a sense of how this was, how it actually accumulated, at each time interval that we looked at. So this is the same data, just shown a different way. So this is on the y-axis, the vertical discrepancy. So this is the amount I had to correct the bathymetry. And then this is time on the x-axis. So you can see these little kind of black nubby lines early on. These are all within error. There's no discrepancy there until we hit the early Cretaceous, when we see this really big jump, and I had to adjust it to get it up to the correct bathymetry. And then there was another big jump in the Jurassic. So these highlights these 2 time periods where something was causing vertical movements that are not accounted for with any obvious corrections. All right, it's not within error. It's on the order of 500 meters to 1 kilometer at each of these different times. So it doesn't seem like it's user error, but I wanted to still rule out a few things, like what could be actually causing this. I wanted to make sure it wasn't an issue with the model inputs, because this is of course a model. So in the interest of time, I'm just going to say that I tried a lot of things to get this to the correct bathymetry. I tried increasing the mud content of the sediment because that would affect the decompaction and therefore, how much the units are brought up at each time step. I tried changing the beta factor, and in general, just changing any inputs I could to see if any of this would solve the problem. And in short, it didn't solve the problem. Not even close. So what you're looking at here, this black line, is where the basement should sit, right where when salt was deposited. And here's where the lines actually sit if I don't apply any corrections. And these are sort of two end members, one with, a high beta factor versus a low beta factor and higher mud content and things like that. Those things only made a difference of a few hundred meters. It did not solve the problem. So we think that these vertical anomalies are real now. We don't think it's some sort of user error or incorrect model inputs, which led to the question, what is causing hundreds of meters of anomalous vertical movements in the Mesozoic Gulf of Mexico? Well, we are now pretty convinced this represents dynamic topography. So mantle dynamics like upwelling and downwelling, these can cause really long wavelength, short amplitude, topographic changes. These forcings are often very difficult to observe, but observations like I've shown, these anomalous vertical movements, these can help test dynamic topography hypotheses, these types of observations. So what was going on in the Gulf of Mexico in the Mesozoic? Well, one potential source for dynamic topography in the GOM is the Central Atlantic Magmatic Province, or CAMP hotspot. So CAMP is most well known for producing an expansive large igneous province about 200 million years ago. But an important point about the CAMP is that it represents a period, the large igneous province itself represents a period of hyperactivity on what was a very long-lived hotspot. And the hotspot itself can produce vertical movements even when it's not generating a large igneous province. So this tectonic plate reconstruction I'm going to show here, this is from Colin Reeves at Earthworks. It starts at 170 MA, and you can see CAMP highlighted right here. And then this is Florida and the Gulf of Mexico. So I'm just going to show you how that sort of evolves really quick. And then I'm going to kind of bring it back like that. So you can see from 170 to 160 to 150, the CAMP hotspot was right on top of or very near the eastern Gulf of Mexico during the mid to late Jurassic, which is where we're seeing these observations. Furthermore, it turns out there's evidence for magmatism in the mid to late Jurassic in the eastern GOM. You guys are quite fortunate because you're going to get to hear, I believe, more about this in the next talk by Jim Pendell. So all I'm going to say here is that I'm going to highlight here that there are igneous rocks that were of the correct age in the Gulf of Mexico, in the eastern Gulf of Mexico, right when I'm also observing these vertical movements. And you see it again in a little later on as well. I'm not going to dwell on this because I think you're going to hear a lot more about it in the next talk. So take home point here, the CAMP hotspot was near the eastern Gulf of Mexico in the mid to late Jurassic. There's evidence of magmatism at that time. So it is at least plausible that the CAMP hotspot managed to sort of keep the eastern GOM high and then drop it low and maybe be responsible for these vertical movements that we're observing. So with that, I will just say that the conclusion here is we documented 500 to 2,000 meters of unexplained vertical movements in the Gulf of Mexico in the Mesozoic, and we believe these are reflecting CAMP-induced dynamic topography. And I'll leave you here with some of the images of the structural restoration that I did end up undertaking as part of this, even though I didn't talk a lot about that today. And I'll just say thank you and take any questions.
Awesome. Thank you very much, Maggie. Does anyone in the audience have any questions for her? Okay, looks like Sasha has one.
Hi, Maggie. Very nice talk. When I see talks about the South Atlantic salt basin, people discuss an enclosed embayment where the local sea level is different than the eustatic sea level. Could that be an option here as well?
Yeah, I mean, there's been a good bit of work trying to understand what the sea level was like in the Gulf of Mexico, particularly when the salt was deposited. But the thing is, we do have, pretty good evidence about the depositional systems. And, for example, if you have carbonates being deposited, there was water there, so you have some constraints even on the local sea level at that time, right? Mm-hmm. So because of that, we feel pretty good that even local sea level was but how do I put this? We know that the sea level was at least as high enough to sort of drown that margin by the end of the like shortly after the salt was deposited, because we see those carbonates deposited there. And so even if it was just the local sea level that was high, we're still seeing, okay, like, you know, it seems like, you know, a kilometer or two is sort of unreasonable to expect that the Gulf of Mexico was dropped down with respect to the, you know, sort of the rest of the globe. So, I mean, it's a fair point, and I don't think we have like a very good, like precise idea of what the local sea level was, but my feeling, and from what we've done here and what we've read at least, and what other people have said, is, you know, it's not enough. It's not enough to really explain this. It seems like this might be a real observation, that there was really something sort of affecting the vertical movements here at this time. But I'm not going to lie, this was a bit of a mystery for a while.
And there are other places like in the North Atlantic where you have evidence for similar vertical motion that cannot be due to any local sea level changes. So where people also think it's dynamic topography. So I believe it.
Yeah.
Awesome. Thanks. I think we have a question from Mark Rowan. Please unmute and go for it.
I hope you can hear me. Just a point of clarification. You talked about the middle and late Jurassic. How far back did you actually go? Was your last restoration step going back in time to the top salt, or was it some of the strata above it? Can you just clarify, please?
Yes, I can. The last step of the restoration was the top of the salt. But I would say by the time I got to I would say the last one I feel most confident about would be like the top of the Smackover. So I'm just going to back up here. Yeah, we'll do this one. So you can, maybe we'll go back one more. No, we'll do this one. This one's bigger. So you can see way back here would have been the top of the salt. And then this would have been top Smackover and so on. So the last one I feel really confident about the paleobathymetry is the top of the Smackover. Although we did restore it back to salt, I would say going from Smackover to salt, there's a lot more uncertainty in terms of what that sea level was doing. But when you get to the Smackover, you know, you're looking at carbonate. So,
and just a related note, what age is used for the top of salt?
165.
Okay, thanks.
165
Derek?
MA.
Thanks for the interesting talk. I've got a question about the, are there any constraints sort of on land of, you know, evidence for anomalous uplift during the time period of interest, you know, the sort of continental side of the system?
Yeah, it's a really good question. I can't think of anything to my knowledge right now, but I should definitely look into that. Yeah. You know, I might be sort of stepping out of my my realm of knowledge here, but if I go back here, you know, we were looking only on, you know, our line started on the carbonate platform. So we were really only looking, you know, it was subsea for almost the entirety of these restorations. It was you know, or submarine. But yeah, I couldn't say right now. I'm sorry, but that's a very good question.
Just a quick, there was a bit of chat going amongst the conveners about the sort of the crustal thickness that you assumed at the starting point of the model, or how did you constrain that? Because it looked like, I just noticed it sort of still seems to dip on the sections you showed. So I wondered whether you used
so we used seismic observation. So there's really a really deep seismic survey in the Gulf of Mexico. That the goal of shooting this was to image the moho sort of all over. So we managed to get our hands on that one. So we had the moho mapped pretty well. I might have a backup slide about this. Let me see. Yeah. So this is mapping that we did as part of this study. So this is the crustal thickness measurement. So we had the moho, and we took the base of the salt, the sort of beginning of the Mesozoic sedimentary section as the top of the crust there. And then we mapped the moho using this very deep seismic survey. So, you know, up here, you know, we kind of assume it's largely on extended crust, and it was about 35 kilometers thick. You can see that right here. So that was the most reasonable crustal thickness that I used. I tested some pretty unreasonable crustal thickness values as part of the sort of sensitivity analysis to see if that could be driving the vertical sort of discrepancy. And it didn't seem to. So I feel pretty good that this is the true crustal, sort of unextended crustal thickness there, but
Okay.
people might disagree.